Good evening. My name is Dave Perry. I'm giving a presentation from my master's. My project is entitled Using LiDAR for Urban Change and Analysis, and I'm looking at the University of Arizona in the years 2005 and 2008. Tonight I'm going to go over my outline. My first thing I'm going to talk about is the purpose for doing my study. I'm going to briefly explain the study area, give a background on LiDAR, talk about the data set that I used, go over my analysis, talk about my result, and talk about my conclusions. The purpose of this study is to test the feasibility of using LiDAR, which is short for light detection and ranging data, to identify and illustrate change in an urban environment. In my case, my urban environment, meaning an environment where there's buildings as opposed to a rural environment, is where we are right now at the University of Arizona. The study area that I'm using is the campus of the University of Arizona. It's delineated by Speedway on the north, Campbell on the east, 6th Avenue on the south, and I went all the way to Euclid on the west. LiDAR. As I said earlier, LiDAR stands for light detection and ranging. There are several types of LiDAR. The LiDAR that I use is called discrete LiDAR. Discrete LiDAR uses small beams of laser light to identify the distance between the sensor and the target that you're looking at. There are several types of discrete LiDAR. One is ground static LiDAR. In this case, it's normally a unit like this that's mounted on a tripod. You can put it anywhere you want to, and you can image the buildings, the terrain, whatever you want to see around you. Another type is ground dynamic LiDAR. That's LiDAR that's mounted on a truck excuse me, and is moving. And it's amazing how fast you can move and pick up a tremendous amount of data doing this. And then the third type is the type I used, and that's aerial LiDAR data. Aerial LiDAR data, as the name would imply, is flown from an airplane. There are several components that are necessary to get an accurate LiDAR map. The first is the laser scanner itself, the laser sensor. In this case, a discrete LiDAR sensor. It's mounted underneath the plane and shoots out beams of laser light to the ground, to the targets. It's reflected back up again and measured. Now, it's extremely crucial when you're doing this to be able to identify where these points are in space. So in order to do that, there's three systems used. The one is something called an inertial navigation system, which is directly coupled to the LiDAR device itself. This is actually a self-contained system that relies on accelerometers and things to see from where you started to where you are. So it's a self-contained system. Then the other system is the famous GPS that we're all familiar with. In this case, there's two types of GPS used. It's called differential GPS. There's a unit that is on the airplane itself that's really part of this entire unit here. And then there's ground GPS systems. There's ground systems all over the flight area. And these interact with the GPS there to get a very exact reading as to where that particular point of light is measuring. The data you get is called point cloud data. This is a point cloud of the University of Arizona. And to be more specific, this is what the student union looks like, which is where we happen to be right now, in the student union. You can visualize this LiDAR data in several different ways. The way I think is kind of interesting is called a profile view. This is a profile of the building we're in right now, the student union. In fact, this is a profile of the room we're in right now, the Ventana room. The beauty of LiDAR is that it allows you to get depth data. So unlike just traditional remote sensing data where it's basically two-dimensional, this has three-dimensional data. And that's what I did to allow me to pick out ultimately the buildings I was looking for. The way it does this is you can get different kinds of what are called returns. Trees and plants provide something called soft returns. There are first and last returns, hard returns off of roofs, off of surfaces, off of the ground. This would be a last return off of the ground. So you can get different returns, up to 5 different kinds of returns in any LiDAR overfly. So the data that I used was from the Pima Association of Governments LiDAR database. This is a database that's available free to people within the university through the library system. The Pima Association of Governments got this. They commissioned the Overfly. I used 2 data sets. One was from the year 2005. It had, when we talked about returns in the earlier slide, this had first returns and last returns. And then 2008 had first returns, last returns, and also intermediate returns. But since the 2005 data only had first and last returns, that's what I was limited to using. And for the geography stuff, this is NAD 83. It's projected in Arizona State Plains Central International Feet. This is a general analytic scheme that I use to analyze the data with. The first thing I did was I took the PAG LiDAR data set, which is all LAS data, it's in the LAS file, and I converted this in ArcGIS to a raster. And then from here on out, I was working with traditional raster data. And I did the series of raster manipulations that I needed to get to based on the different return types, and came up with a raster for the University of Arizona buildings in 2005 and a raster for the University of Arizona buildings in 2008. And then I did a change analysis to determine what buildings had changed. So this is a raster they came up with for 2005. You can see that the university buildings are all highlighted in red. And this is the raster, it's a little bit different, but that I came up with for 2008. These are all using the same thresholds, the same values, so I came up with the same buildings essentially. The big problem I had was trying to figure out how to analyze change. A lot of people thought a way to do it was to look at percentage change over those 2 time periods. That was useful, but I thought it wasn't very helpful because it didn't allow me to identify specifically where the change had been. So I used a big sounding word of Boolean algebra. Boolean algebra is where you take true-false statements, and essentially it's used a lot in computer science because it does use ones and zeros, and you can put everything into ones and zeros. So what I did was I took from my 2 rasters that you saw earlier, for the 2005 and 2008 raster, wherever there was a building, I put a 1. Wherever I reclassified it as a 1. Wherever there was not a building, I reclassified it as 0. And then I did raster math with it. So I came up with the final change raster had zeros where there had been no change, a -1 value where there had been a change, and a +1 value, or -1 value where there hadn't been a change, and a +1 value where there had been a change. So this is kind of graphically showing what I did. I took 2008 and I subtracted it from 2005 and came up with a resultant raster. This is 2005, and I get my change raster. And I was able to identify 5 major buildings that had been built during that 3-year period. The first is the architecture building. The second is there was an addition to the softball facility. The third is there was the Wilco building, which was built at the corner of Park and University. The fourth was they added a diving well to the Hillenbrand Aquatic Center. It's a little bit harder to see because it wasn't as high as the other buildings were. And then the last was they added an addition to the Cherry Street garage. So in order to make sure this was really what had happened, I went into the orthophotography, very high resolution photography that was also taken at the time that the LiDAR overfly had been done. And with that, I was able to confirm, in fact, that these 5 buildings had, in fact, this is a 2008 ortho photograph, had in fact been built in that time frame. So the future. For an area as small as the University of Arizona, this seems like a fairly trivial process. You can just look at the photographs, see what the change has been. But in an area where it's not so small, an area like Manhattan, Berlin, Chicago, Shanghai, Tokyo, London, or a city like Moscow, this way you can use this same analytical scheme to identify where, not only that there's been change, but where the change has been. And this is very useful for people interested in things like urban planning, what buildings have been demolished, what buildings have been built. And oftentimes people who are tax assessors in those areas also want to know similar information. So this provides a much easier mechanism than actually studying the ortho photographs and trying to identify where there's been change over any year time frame. So in conclusion, I was able to show that in fact you can use LiDAR data. It provides, once you've kind of got the mechanism solved, the analytical scheme solved, provides a very time and cost-effective way to show change and also identify where the change has been. And as I said earlier, the ability of LiDAR data to provide elevation information is what allows this to work. So in conclusion, I went over the purpose to see whether you can use LiDAR data to illustrate and visualize change in an urban environment. I went over my study area, the U of A. I talked a little bit about the background of LiDAR data itself, talked about the data set that I used. I showed my analytical scheme, my results, and talked about my conclusion. These are the references. Any questions?